What we did in the last lecture was that we tried to explain. We wanted to understand what the image method is. That was the last topic of the chapter related to electrostatics, and we solved an example related to that topic too, in order to understand how to calculate the value of E if we have been given a charge which is displaced by a distance d from any infinitely conducting medium, and we calculated the value of E by using a reflection of that charge and by eliminating that conducting medium with the help of the image method. After that, now we moved on and we discussed about some basic two basic postulates of Maxwell equations that were related to magnetostatics, and then we tried to give a little bit of detail about how the value of B and H are related, and we said that they are related linearly for maximum materials, but in case of ferromagnetic materials, due to saturation, there comes a point when the value of B is not linearly related with the value of H, which is magnetic field intensity essentially. After that, we basically had a look that why do we need to study these uh, uh, this topic of magnetostatics, and the objectives, basically the applications of this chapter. And now we will try to move on to the next topic, which is magnetic forces and torques. So, as evident from the title of this lecture, we will be talking about the magnetic forces. First of all, we need to understand what a magnetic force is. The counterpart of magnetic force in electrostatics was basically electric force, which was Fe is equals to QE, if you can remember, reflecting back to the electric force. Now we need to know what magnetic force is. So first of all, we will tender our attention towards the concept of magnetic force, and once we have the understanding of what a magnetic force is, then we will use the concept of that magnetic force in order to understand what the torque actually is. I know that you have studied torque in metric and FSC also, but we will try to uh, dig deeper into that concept, and we will try to take in that concept of torque more efficiently, so that you know what the value of torque basically depicts, because it will be used in the next courses that you will study, like electrical machines, in which the torque has a wide range of applications. So as far as the value of, or the concept of electric force was concerned, the electric force, yeah, Fe, that was per unit charge acting on a test charge when it is placed at in the vicinity of any electric field. So now we will try to define what the magnetic force actually is. The magnetic force basically is the force that is acting on a charge when that charge is moving, and it is under the vicinity of any magnetic field, which means that if we have this charge and it is moving with a velocity u, and at the same time we have some sort of uh, magnetic force through which this charge is moving. So as a result, the concept of magnetic force says that when this charge will move with a velocity u under the influence of any external magnetic field, there will be a force which will act on this charge, and that force basically will be the magnetic force. And based on experiments, the value of that magnetic force was calculated to be q into u cross b. If we take a look, as this is a force, so the unit of this will be Newton. If we take a look at this expression and we try to comprehend this equation in more practical or physical form, then we will see that the direction of this force will be perpendicular to the plane containing the vectors u and the vectors v. That's what we studied about cross product, right? The resultant of any cross product that has to be perpendicular to both those vectors whose cross product we are taking. So if we take a look at this example, in this example, the direction of movement, the direction of velocity is, if we mention this, like this is y-axis, this is z-axis, and this is x-axis. The x-axis is basically coming out of your screen. So if we take a look at this example, the unit vector of velocity is y hat. The unit vector of magnetic field is minus z hat. So the basically the unit vector of the force will be, what will be the unit vector of force? All you have to do is that you have to curl your fingers from u towards this vector. So the unit vector of force will be minus x hat, which will be into the screen. The x was basically coming out of the screen, but if we curl our fingers from u towards b, we will see that our thumb will points inwards toward the screen. That means that the force that will act on this charge, it has the direction of minus x hat according to the reference that we have taken. This was the simplest example that I could give for you to understand how to figure out the direction of this magnetic field. So for any positively charged particle, the direction of magnetic field will be in the direction of u cross b, which is perpendicular to the plane that is containing the velocity and the vector b. And for a negatively charged particle, that force will be reversed, because there will be a minus sign then here, and that minus sign will basically depict that now the direction of this thing is positive. So in case of a negative charge, the value the direction of this magnetic force will be opposite to that case in which the value of that charge was in positive. So this is what was related to the direction. And if we want to talk a little bit about the magnitude of this force, that means that we are talking about u b sine theta, and this theta is basically the angle between u and b. This is the angle between the velocity and the magnetic field, and this is the angle between this thing and the magnetic field. So we will see here that in order to make our magnitude maximum, the magnitude of this force will be maximum whenever u and b, they are perpendicular to each other, and it will be minimum when u and b, they are parallel to each other. Minimum meaning they will be zero, because we are talking about cross product here. And if these two things are perpendicular to each other, then the magnitude of this force is going to be maximum. And when these two vectors are parallel to each other, the cross product will be zero, and the force that is acting on this thing will be zero. So in order to make this magnetic force zero, uh, either your velocity has to be zero. That means that if your charge is not moving, even if it is placed under the vicinity of any magnetic field, the value of force acting on that charge is going to be zero, because the velocity here is zero. This makes this cross product zero, and this zero, when multiplied with this charge right here, this will make this fm is equals to zero. So if the charge is in rest position, there will be no magnetic force acting on it. Apart from that, if the charge is moving but there is no magnetic field, so then again, as there is no magnetic field, there will be no magnetic force. Once again, the fm will be zero. And if the value of charge is zero, that means it is not a charged particle, it is a neutral particle which is moving through any external magnetic field with a velocity u. In that case too, the value of fm will be zero. So we talked about the maximum magnitude of fm, we talked about the minimum magnitude of fm, the zero magnitude of fm, and we try to understand what the fm actually means, the magnetic force actually means. So if a charged particle is under the influence of both b and e, now there comes another situation in which we have b and we have e also. ठीक है? So under this kind of scenario, what will happen? Do we only have the magnetic force, or do we now have the electric force too? So the answer to this question is that we will have both of these forces, because now we have a charged particle and we have an electric field. So as a result, there will be a charge, there will be a force, the electric force, which will act on that particle. Apart from that, if that particle is moving and there is an external magnetic field too, there will be another force, which is Fm. So now there will be two forces that will be acting on this kind of charge. These two forces will add up to be Q into E plus Q into U cross B. These are the two things. We can take Q to be constant and E plus U cross B. Now this kind of force is called Lorentz force. We know that we have studied this in FSE or metric also. So the Lorentz force is basically the sum of electric force and the magnetic force that is acting on a charge under the vicinity of both electric as well as magnetic fields. So this is the Lorentz force. Now if we talk about what are the difference between Fe and Fm, what are the differences between these two forces? Now we know that Fe is always in the direction of electric field. We know this because Fe is equals to QE. Q is a scalar quantity here, but whatever the direction of electric field is, the Fe, the direction of force that is acting on that charge, will always be the same. Okay, so Fe will always be in the direction of E, but the Fm, this is always perpendicular to B, because we know that Fm is basically the cross product, the resultant of cross product of U and B, which means that the resultant will be perpendicular to both U as well as B. So this is the first thing. Now Fe acts on a charge even if it is in rest. Fe acts on a charge in rest position, but Fm, that only acts on a charge when it's moving. So this is the other difference in between these two forces. Fe expends energy while displacing a charge. Fe basically expends energy while displacing a charge, a charge Q. But Fm, this does not do any kind of work. No work. Why? The reason is that if we go back to this example, we had a charge, it was moving in this direction. This was the magnetic field, and we figured out that the direction of Fm was inwards into the screen, which means that the motion is in the direction of y. Basically, if it is moving this way, the dl will be in this direction. So the motion is in the direction of y, but the force, that is basically in the direction of minus x. Okay, so minus x dot y, x hat dot y, these two things are mutually perpendicular, and as a result the work will be zero. So there will be no work done by magnetic force. All a magnetic force can do is basically change the direction of this motion, the motion that was under the influence of any external electric field. It can change the direction, because you know that if a charge is moving in this direction and you apply a force in this direction, then this force cannot accelerate or decelerate this charge. All it can do is basically it can change its direction. If it was to go this way, now in under the influence of this magnetic field, it will start moving a little bit, it will start deviating from its usual path. So all it can do is it can change the location, but it change the location or change the path that it is following while moving, but it cannot do any charge, it cannot do any work, it cannot accelerate or decelerate, because in order to accelerate or decelerate a charge or any object, you have to apply the force in the direction of the movement of that thing, or in the direction which is opposing the movement of that thing. Just like if you are pushing a car and you want to move that car, and once you start pushing, the car starts to accelerate. So the force that you are applying while pushing that car, in order to move that car, that will be in the direction of that movement, that will accelerate that car. And if you want to stop a car, you will apply a force which is opposite to the direction of motion of that car. If you if there is a car and you start you had to move it like this way, but you start applying a force to the side of that car, it will not do any kind of real work that needed to be done. So this is the thing about magnetic force. This magnetic force is basically, it can only change the direction of motion, but it cannot change the kinetic energy of a charged particle, because it isn't doing any kind of real work. But B can change the direction of a motion of a charged particle, but it cannot change its speed, its velocity, or it cannot accelerate or decelerate that thing. When we talk about accelerating anything, we surely talk about changing the velocity of that thing. And if we talk about decelerating that thing or stopping that thing, once again we're talking about changing the speed of that thing. So you need to understand and you need to keep this in mind, that Fm will not ever change the speed or velocity or acceleration, or provide any kind of acceleration or deceleration to any charged particle. All it can do is that it can change the direction of a motion of a charged particle. Okay, so taking this concept and applying it to a more practical scenario, that means we will be taking another example, and in that example, let's see, uh, we have this conductor right here, and we have an electric field. This conductor is placed under the influence of, sorry, not electric field, but it is placed under the influence of an magnetic field. Now when we talk about cross, we are talking about the direction which is into the screen right here. The thing Yeah, the way to remember this is, you know, that when an you see the arrow from the back of his, uh, you know, there is an arrow like this is an arrow, this thing. When you see an arrow from this direction, you will see this cross, and whenever you see an arrow from this direction, you will see a dot coming out of that thing. So whenever we are talking about, yeah, whenever it is mentioned a cross in any book or in any scenario, this means that we are talking about the direction which is going into the screen. And whenever there is a dot right here, it means that the magnetic field is now coming out of this screen. So the dot is basically the head of this arrow, and the cross is actually the tail of this arrow. So now if we say that the reference frame is like this, we have y, we have z, and we have x. X is basically coming out of the screen, so we will say that now the direction of b will be in minus x hat direction, because the direction of b is into the screen. Whenever there is no current in this conductor, there will be no force. Why? Because there is no movement. There is charge, because this is a conductor and there will be free electrons, but there is no movement of those electrons. The total sum of these velocities will be zero, as we talked about this earlier in the conductor portion of our last chapter. So the Fm will be zero at this point. Whenever there will be a current which is passing through this scenario changes. Like what? We will draw that scenario too. Here is the scenario in which now there is some kind of current which is passing through this conductor. Now we need to know that what will be the direction of Fm. Will this conductor remains in this position, or will it deviate from its path? Whenever there is a current, and we will say that the current is basically going upwards, in that condition we need to know what will be the direction of Fm. So in order to calculate the direction of Fm, we know that F is equals to Q into U cross B. If the value of, yeah, the direction of current is upward, when the current is upward, the wire deflects to minus y direction. Why? Because the u is basically now in z's direction. तो u की direction जो है वो z के है, cross, what is the direction of b? The direction of b is minus x hat. So as a result, what will be the direction of Fm, which is the cross product? This is minus y. That means that if this is y, this is minus y. It means that there will be a force which will act on minus y direction, and our conductor, if it's a little bit flexible, it will deviate like this. Okay, so this will be the direction of Fm here. Now if the same thing happens, but now the direction of current is downwards, so what effect will it have? Now the direction of motion, yeah, the direction of velocity is in minus this direction, and the direction of b is once again at minus x hat's direction. As a result, the direction of Fm will be in plus y. So if the movement of current is like this, then the value of Fm will be in the direction of y hat. So this is how basically the magnetic force acts on a current carrying conductor. Now he says that in order to quantify the relationship between the current I and Fm, let's consider a small segment of a wire with area. He is now considering a small segment of a wire with area A. What is the goal of this thing that we're trying to do here now is that we want to quantify the relationship between I and Fm. Okay, so let's consider a small segment of wire with area A. dl basically is the differential length through which that current is flowing, and we assume that the charge constituting I are only electrons. He's saying that as we're talking about a wire here, so this will be a conducting material, and if it is a conducting material, that means the major contribution in flowing in the flow of current is due to the movement of electrons. So he is saying that let's assume that the charge constituting I are only electrons because it is a conductor. If a wire contain free electron charge density, if a wire that wire contains free electron charge density minus Ne E, and this Ne corresponds to the number of moving electrons per unit volume. We have studied this already. Reflecting back to that thing, number of moving electrons per unit volume, and this is the charge on an electron. Okay, this will be in positive 1.6 cross 10 is power minus 19. This negative is depicting the electronic nature of this thing. So the charge density will be minus Nee, where N is the number of moving electrons per unit volume, and the total amount of moving charge in an elemental volume will be, if we want to calculate the value of total charge, that is moving in an elemental volume, that will be rho v e dv. And if we want to implement this onto this segment, so what will be the volume? The volume will be area into differential length. Area into differential length. So we have replaced this dv with area into differential length, because area is constant, and then the current is moving through that differential length. And rho ve will be minus ne into e, that is the charge. So now the dq, the total charge, is minus ne e a dl. This is the value of dq. Now we do have the value of total charge that is moving through that elemental volume. The basic uh, goal of this activity was to quantify this relationship, the relationship between fm and q, for this scenario, this elemental scenario. So now the charge on this, the force on this charge which is moving through this wire of segment of wire of area A, with this will be is equals to dq into ue cross b. Okay, so now the value of dq is minus ne e a dl, and inside there is ue b. But if we reflect back to this thing and we compare it with this expression, this u was basically the direction of conventional current. On the other hand, this u is basically the direction of electronic current. So there is something wrong with this equation. We need to uh, change this equation. Okay, so what he's trying to do here is that he is trying to convert this vector form of velocity into its scalar form, and then he is trying to convert this scalar dl into its vector form. How can he do that? In order to accomplish his goal, what he is trying to do is that dl ue minus, if we take these three things, minus dl and then ue, this is equals to, if we break down this ue and we write it in the form of unit vector, that is a, so we know that the dl is basically, this is the direction of conventional current. As you know that this current that was flowing through this wire, we asked a little bit segment of this, and the value of dl will always be in the direction of current. So this dl is basically in the direction of conventional current, and in order to change this dl into its vector form, we need to have a direction which is opposite to the direction of this ue. This a hat is basically depicting the direction of velocity. अब जो velocity की direction है उसके opposite dl की direction होनी है, क्योंकि वो आपके पास conventional current की direction है. तो अगर हम कहें कि ये minus a hat dl and then we will write this ue, so this is now the direction of the actual dl, the direction of conventional current. So this is dl vector and this is ue. Okay, so he converted this equation into ne e a ue and then inside the brackets dl cross b. So this is the quantification of the relation between dfm and the charge that is contained. The goal is not achieved yet because we need to simplify it a little bit, because we do not always have the value of ne, the number of charges that are flowing per unit volume. We do not always have the value of a. We have to convert this thing into its more generic form. And we know that when we want to convert any expression in its more generic form, then we need to express that expression in the form of an integral, so that we can calculate that integral for any kind of shape. So in this case, he says that the current flowing through the area A due to rho VE minus NEE is moving with velocity minus UE. That current is basically, if you reflect back to the thing that we studied, was J is equals to rho into U. Okay, and I basically was equals to J dot ds. So by using these two equations, we can say that the value of I will be rho ve, okay, the charge density, into minus ue, that is the direction, and we have put the value of j rho ve into ue, and now we need to put the value of ds, that is total area. Okay, so we can rewrite this as, what will be the value of rho ve minus, what's the value of rho ve, is minus ne into e, and then we have minus ue, and then we have a, so that comes out to be ne e ue, and then a. So this is equals to I, and if you see, we have NEEA or UE right here. So we can rewrite this expression as DFM is equals to I into DL cross B. And if we want to convert this into a more generic form, then for that case, it will be Fm is equals to I integral of closed contour of dl cross p. So this is going to be the quantification of the relationship between the magnetic force that is acting on a current carrying conductor. So this is the current, the dl is the path that the current is taking, the b is basically the value of magnetic field, the magnetic flux density under the influence of which this conductor is placed. And if we put all these values into this equation, then as a result we will be able to quantify, we will be able to accurately calculate the value of magnetic force that is acting on this thing. So the goal for our today's lecture is accomplished in this by this derivation of this expression. Okay. Now there is an example. In this example, he says that he has a closed loop and there is a current that is flowing through this closed loop. This closed loop is placed under the vicinity of a uniform magnetic field. This uniform magnetic field is basically referred to as B. As you know, that this is the current and it is a closed loop. So refer to this figure. If we want to calculate the value of Fm that will be applied on this conductor under the vicinity of any magnetic field, uniform magnetic field, which was mentioned here. So this is a closed wire basically. This is a closed wire. The current I is flowing through it and the value of B is uniform. So the value of B is uniform. It means that the value of B is constant everywhere around this thing. So if we want to calculate the value of Fm, we have the expression dl cross B, and we have already said that the value of B is uniform, which means that the value of B is essentially constant at every point. So we will take this B out of the integral. All that remains is the closed contour cross it will be much better if we can place this bracket here. Okay, so we took the b out of that integral because we said that the value of b is constant throughout. Now we know that if we calculate the value of dl for a closed path, the value of dl for any closed path will always be equals to 0, because if we started from here and we calculated the value of dl for this whole path, then we know that we will end up right here. That means that we haven't gone through any displacement. So we have studied this concept in the conservative nature of electric field. If you reflect back to electrostatics, uh, we knew that whatever the path we took, it doesn't matter, because if there are these 2 points, if we take this path or if we take this path or if we take this path, the essential thing is that we have to reach from this point towards this point. If we calculate the integral, it will always be equals to this displacement vector, which is, if we say, small l. Okay, so whenever we will go from here and then come back from here, the dl integral for this closed path will always be equals to 0. So this is the thing he's saying, that for a closed path the value of dl will be 0, so as a result the value of fm will also be 0. So you need to understand this thing is, what you need to understand about this thing is that whenever you have been asked to calculate the value of the force, the magnetic force that is acting on a closed loop, you will know that I'm not saying that you won't need to calculate the value for any segment of that thing, but if that is a closed path, you will know from the start, from the scratch, that the result of that numerical has to be 0. So there is another thing, there is another part in which he says that the current in the curved wire, and it is also under the influence of any uniformed magnetic field. This was the example. So he's asking us to calculate the value of fm for this thing. If the current is moving from point 1 to point 2, he is not saying that the current is moving from point 1 to point 2 and then coming back from point 2 to point 1 through any through any other path. He is only asking us that if this is the path from point 1 to point 2, and there is a current flowing from point 1 to point 2, and there is some sort of a magnetic field in which this conductor is placed, he is asking you to calculate the value of fm which will be applied on this conductor as a result of the movement of this current. So for that case you will calculate the integral, but once again the b is uniform, so it will come out of the integral, and the integral of dl will be from point p1 to point p2. Okay, so if the distance between these 2 points is given to be small l, then the value will be I p2 minus p1, p2 minus p1 will be equals to l. So this integral will solve out and it will be equals to l, and then this. So this is the value of fm if you are going from point p1 to point 2 p2, if your current is going from point p1 and to point p2. Now if he says that that current from is coming back to point 1 by following some other uh, path, then for that case, for this case the value of fm was this, and for this case the value of fm, when you compute it, when you compute this integral for point p2 to point p1 by using this curved path, you will see that the value will come out to be I in minus I into L cross B, and the total force will be Fm1 and Fm2. F total will be Fm1 plus Fm2, and that will come out to be 0. So there will be positive force that will be acting on this thing, and there will be a negative force that will be acting upon this thing, and as a result the total force will be 0. So whenever the current is flowing in a closed loop, the total magnetic force that is acting on that closed loop will be equals to 0. And if you are asked to calculate the value of a segment, then it will certainly have some kind of value. We will solve another example in the next lecture, and this concept will become even more clearer when we solve that example, because in that example we will have a semicircular loop, and for semicircular loop, uh, because it is a loop, it will come back to the point where it started. So we will break down into we'll break down that semicircular loop into its two segment, and we will see that how these two different kind of segments will have the same but opposite force acting on them. So this is it for today. If you have any questions, feel free to ask them in the interactive session. Thank you so much.